Today we're joined by the most excited thermal engineer in the industry. When are you doing 4/3 blow through? When are you breaking the laws of physics?
I can't talk about that one. Unreleased. Okay. That's another prototype you'll get.
This is Malcolm Gutenburg from NVIDIA, who previously joined us to cut an RTX 4090 cooler in half for science. This time, he served as the lead thermal engineer on the RTX 5090 Founders Edition, and he brought a lot of prototypes and a lot of vocabulary.
This is a pure aerodynamic change. So coefficient of thermal expansion. Application of thermocouples is an art. Hermetic seal rubber gasket here, heat of vaporization. You can actually calculate the mass flow rate based on the power, even ampere. We started looking at liquid metal. Redirect the airflow away from the inlet of the fan.
In this video, Malcolm shows us liquid metal on the RTX 5090, the design and the considerations around it, a world first with a horizontal 3D vapor chamber piping structure, and we learn about aerodynamics and thermal design. Let's get into it. Hey everyone, I am joined by Malcolm, thermal engineer and thermal evangelist at NVIDIA. Malcolm, you've joined now for, I think, 3 videos.
Yep.
Every time Malcolm's been on, he has brought a box of mysteries, and this time there was a very large suitcase of mysteries. So this is for the 5090. We're gonna go through a lot of stuff today, but Malcolm, if you could help walk me through a few of the things on the table.
Sure.
To give people a primer.
Yeah, 5090, thermally, it is incredible what we've been able to achieve. And this is kind of the evolution on how we got to 5090. So obviously 4090, we have some, very early flow and acoustic samples here. And then new this generation is a 3D VC. So here is kind of the evolution of the 3D VC from its very early infancy through towards the final 3D VC.
VC here meaning vapor chamber.
Vapor chamber, yeah. And this here is the incredible 3D VC where the heat pipes directly connect to the vapor chamber, featuring a new artery wick in the evaporator area.
Yeah, I'm not sure if the shadow will help the camera see it, but there's some really slight, what was the difference, the delta?
About 300 microns.
Okay. So there's like 300 micron height difference in the, is it accurate to call it sintered powder?
Yeah, this is sintered powder, and this is also using 3 different types of wick. So we have the braid wick, the sintered powder, and then a mesh wick on the top cover.
Okay, very cool. And then this is a test vehicle, I guess?
Yeah, so this is one of our test vehicles here. You can see all the thermocouples miraculously weaving their way through to each component. And then, of course, liquid metal thermal interface material with a triple barrier gasket there to ensure it's reliable, make sure you can use it in all orientations, shock and vibe, throw it around.
And there's more back there too. So there's a lot of stuff. Before that, this video is brought to you by Height and the Y70 case. The Height Y70 case has a lot of polish and heavy attention to detail on the finer points. The case can fit radiators that are massive in depth to the side mount, has cooling in the floor of the case for direct intake to the GPU, and tries to find a balance between structural support of dust filters without obstructing too much intake. The Y70 is a follow-up to the popular Y60, which got Height to where it is today with its cut corner tempered glass cases. Objective for this video really is just to talk about how this stuff works and some of the design process, but same thing we did with the 40 series, except now there's a lot of new topics. And we just took apart that unnamed card on the channel recently. To me, there's some stuff here that's familiar to that. The performance on that card, I've been telling people at the show here, is really the only reason that I have any faith, speaking honestly, that a 2-slot card can do 575 watts.
Yeah.
Because the performance on the prototype was so crazy. And granted, that's bigger. If there's some of the same principles applied, then I think that's where it gets interesting. So
the whole architecture kind of revolutionary concept this generation is dual blow through. So both sides of the heatsink, the airflow directly goes through, which basically means it doesn't have to turn in order to exhaust out of the graphics card. And what that does is it reduces pressure drop, increases airflow, reduces temperature, reduces acoustics. The really beautiful thing about blow through, and obviously you've taken apart our prototype, and there's a video on that. And when we look at the prototype, the reason it had to be 4 slots wasn't because the thermal solution necessarily needed 4 slots. When you look at it, you can see the fins are very wide. They're far apart, and even though it is 4 slots, really thermally, you don't need all that. It was more because the PCB, the GPU plus memory, the stack up was 4 slots. So if we want to rotate the PCB and have what we call 3/3 blow through,
Okay.
or 100% blow through.
Okay, I see. I was trying to follow the 3/3.
3/3.
Why 3/3? Why not 4/4? Is it because 3 fans?
This was always 1/3 blow through. We always call it 1/3 blow through.
So you work up from there.
Yeah,
Got it.
2/3 blow through, and then 3/3 blow through.
When are you doing 4/3 blow through? When are you breaking the laws
I can't
of
talk
physics?
about that one. That unreleased. That's another prototype you'll get. Anyway, so basically, when you think about designing the thermal solution for any graphics card, you want to look at each resistance. You want to minimize each resistance, and the biggest resistance is always airflow. So there's 2 ways to really increase airflow, and they both have to do with reducing pressure drop. So one way is if you have a traditional PCB. You can make the card, 3, 4 slots, and that gives the airflow more space for it to flow out, as it changes direction 90 degrees. And the other way is with blow through. So with blow through, the beauty of blow through, the real peak of blow through, is being able to make things smaller. So in this one, you can see, compared to like the prototype, compared to 40 series, the fin pitch is much thinner.
Right.
And so we only have about 1.5 millimeters fin pitch.
Okay.
And we can fit a lot of fin surface area and a lot of effective fin area underneath the fans.
So I guess the PCB ends up, I haven't looked at this that closely yet. Is it here?
Correct, yeah,
Okay.
right in the middle.
So there's this ridge where the PCB is. Is this attached to the PCB, the whole PCIe foot?
Yeah, so that PCIe connector, let me get a different word. Here, I can bring it back.
Okay.
So this is the PCB here.
Okay.
And you can see it has a couple interesting things. Well, first of all, incredibly small, incredibly dense compared to the 40 series. But also we have a couple connectors here. So
Power delivery on both sides?
Yeah, power delivery on both sides. So we've actually lowered it into the heatsink. That's why you can see here there's no actual back cover.
Right.
And this is to help with cooling and allowing for tall components on the back.
Okay.
So the backside power components actually increase the overall efficiency of the board. And it's quite incredible. Something we've never been able to do with the traditional PCB level with the back of the heatsink. And then this is your PCIe connector. So that is, we have a board-to-board connector for the PCIe. And then this connector is for the I/O.
Is this custom?
Yes.
Pinout? Okay.
Yeah.
Or well, yeah, I guess because I guess it's just standard PCIe, but you're changing the way it attaches. So.
Exactly. And
okay.
then this one is for the I/O here.
Got it.
So then there's a flex connector connecting the I/O to the main PCB. So in total, it's 4 PCBs that allow for dual blow through.
I'm noticing this indentation here. Is there any meaning for that?
Yeah. So I think that's the most visual change this generation. It looks really cool, and there is a thermal reason behind it. So basically, a traditional fin stack, something like this. So when the fan is spinning, we have a different velocity gradient along the fan from the hub to the outer diameter.
Right.
So basically, although the rotational speed is the same, the tangential velocity is different at each point along the radius. So you have your most effective fin area, or most effective kind of velocity and airflow at the edge of the fan. So what we want to do is we want to maximize the amount of fin area under that section of the fan. So basically what we do is we decrease the fin pitch between every fin. So instead of an optimized, let's say 1 millimeter, which would be a flat version, we change it to 1.5. So we increase the pressure drop, and then what we do is we scoop out that fin under the fan. So we normalize the pressure drop, but we increase the area, the fin area, in that most effective region of the fan.
So towards the outer edge of the, I'll call it the radius or the diameter of the fan, it's getting taller again, and then you're scooping it in towards the hub?
Exactly.
Okay.
Exactly. So of course, below the hub, we have almost no velocity from the fan. So then as we get to the outer part, it's the most effective area. We want all that effective fin area.
So it's interesting, I guess, because the trade-off effectively, it sounds like you're trading off the total surface area because you're losing some height. But obviously what you're gaining from that you think is worth the trade-off of the surface area.
Yeah, you gain surface area in the outer diameter area of the fan. So that
makes up for it?
Exactly,
Okay.
exactly. So, I mean, it's a minor change, but kind of on the pursuit of perfection, you know,
Right.
everywhere. Every aspect of this card has been designed and engineered. you know?
How granular do you get with A/B testing and development? Because like something like this, for example, let's just pretend we had an easy way to swap only this and change nothing else,
Yeah,
right? I mean, other than computer simulation, do you guys try to do practical tests of individual small things like that?
Yeah, for sure. I think when it comes to something like this, it's mostly CFD driven,
Uh-huh.
but then we'll test different versions with the old fin pitch and the new fin pitch. Sometimes there is some sample to sample variation, so you need to be able to eliminate that from your testing.
Okay.
But we do a lot of different prototyping to make sure kind of where we're at
Right.
it makes sense and correlates with the simulation. So this is our our earliest prototype for dual blow through. You can see it's just a block here. So this is non-functional, obviously, but it goes to test just airflow and acoustics.
Okay.
So we want to see what kind of acoustic benefit we get. So this is kind of our earliest prototype. It was actually 3 slots to compare it to 4090 as well. And then this is kind of refines our simulations, refines our design, and then we can dig deeper and figure out what works.
So do you, what do you mount this to when testing it?
So that one we just mounted to a wind tunnel, and then
Okay.
for the acoustic, we did it in the anechoic chamber that you visited. For all the rest of the samples, we actually use something like this, just a metal enclosure to simulate it or to test it in a actual computer chassis.
Okay.
So this kind of gets further along the development cycle. So
Are you doing thermals yet at this
yeah,
stage?
this one is thermally functional. So
Okay.
we're testing the thermal performance, and we're actually comparing all these different ones. And these heat sinks are all slightly different.
In terms of the development life cycle at NVIDIA, I mean, are the PCB guys and the GPU guys even ready for you yet to strap something to it? Or like, in other words, how synchronous or asynchronous are you with the team that's going to end up giving you a PCB at the end?
Yeah, so the PCB team kind of enables this entire architecture. Without the incredible, this dense PCB and all the connections and everything, it wouldn't be possible to do 2 slots, 575 watts. So
I guess you're not off doing your own thing.
yeah, exactly. If we're off doing our own thing, it kind of never ends up in a cohesive project.
Right.
But of course, we don't have necessarily the chip to test and all the diags and all the software. So we do use typically like a heater block to test these ones. But this is all kind of concurrently being designed with the PCB and the overall architecture.
I think you have a
I do have a heater
element.
block.
Yeah.
Should I bring it over?
Yeah, let's do that. So what is this that you're bringing over?
So this is kind of the earliest sample here, and we're still trying to mimic all the different forces from all the gap pads and everything. So we have a PCB that ended up looking pretty similar.
That's very close, yeah.
Quite close, but there's a couple differences. And this will be what we use to test these samples here. So these ones here are going to be tested using heater block, and then as we get further along, you can see this one here. This is one of the DOEs we did.
What does that stand for?
Basically, design of experiments. So we changed very minor things, especially with the evaporator area, which we can talk about as well. We changed, instead of 300 microns, we'll make it 250 microns or something like that. And we'll test a good amount of samples to get a good distribution on how one performs compared to another.
Okay.
So, but a lot of the initial testing is done with heater block, and then we can compare that to our simulation.
So does this end up basically attaching to this?
Yeah,
Okay.
yeah, so this should just fit right on there,
And I guess,
like so.
got it. Cool.
Yeah.
Are you using thermal pads at this stage?
This one should fit.
Okay.
Okay, well, I don't know.
It fits on one of them.
It fits on one of them.
Do you, when you're running that, are you also using the thermal interface material?
Yeah.
Okay.
Yeah. Just to make sure all the balance, all the GPU tilt is correct.
How are you constructing the actual heater? Because I see like these I'm familiar with as like cartridge heaters, I guess.
Yeah, those are cartridge heaters. We actually have a lot of different heater blocks. We have some with some curvature to mimic the GPU die. Here you can see all the cartridges in. We also have some that mimic the GPU heat flux, so we can get accurate versions of like what the dry out point is for a specific vapor chamber.
Got it. How about the next ones down the line?
Yeah, so actually all these are a bit different. So this one here, you can see the heat pipes are flattened a little. We went through different designs and iterations. The real challenge, so this is the first ever 3D VC in a consumer graphics product, but it's also the first ever wing type 3D VC that I know about in the world. So the challenge with a wing type 3D VC, which means the heat pipes are coming out of the side of the vapor chamber. The challenge is connecting those pipes to the main part of the vapor chamber. So we want water to evaporate in the evaporator and then travel to all these different heat pipes and then condense and make their way back. And they do so with this braid wick here. So a lot of these different prototypes here were experimenting with different ways to connect it. This one particularly, you can see here, we actually have the vapor chamber extend, the main body of the vapor chamber extend all the way out to the edges, and then we just directly connect the heat pipes right in. So there's a lot of different variations. We had different size heat pipes, D8, D6.
And on a technicality, I guess, you said there might be like one guy in the world who would bring this up, but on a technicality, these are not, if I understand it correctly, traditional heat pipes like in a CPU tower cooler.
Exactly. So technically, these are either risers or vapor columns, or they're typically called if they come out of the top.
Right.
But in this one, since it's
So
kind of the first
rows,
of its
I
kind,
guess,
you can vapor rows. But since it's a heat pipe is usually one body.
Yeah.
This one is obviously chopped at one end, and then we braze it into the side there.
Right. So then on principle, the way it works, I guess, just strictly for the wicking is what I'm interested in here, but are you running this braid like all the way down the pipe?
Yeah.
Okay.
Yeah, it actually goes all the way to the very end. There is sintered powder in the pipe as well, but it helps connect all that water to come back and flow back to the evaporator.
Other principles the same? I mean, hits the condenser, recondenses, and is it capillary action back to the? Okay.
Yeah, all capillary, and we ensure it works in all orientations as well.
Okay.
So against gravity, all orientations should work.
Got it.
Yeah.
Is there an optimal best case scenario orientation?
Yeah, we always optimize for the traditional user case of horizontal in a chassis, but we also test in all orientations, both reliability testing, shock and vibe, but also thermal testing.
Is there a meaningful difference in orientation for the end user?
Maybe a degree or two, something like that. Yeah, I mean it depends on exactly which orientation you'll operate it in.
Sure. How does dry out, I guess, come into play, if at all, when you're designing like the 3D VC?
Yeah, I mean, so basically it's always this push and pull game of dry out versus overall thermal performance. Because there's ways you can increase the dry out point, but typically those ways also decrease thermal performance. So if you make the wick very thick, it'll have a lot of capillary force, it'll push water back, but you're increasing that resistance. So when you increase that resistance and that thickness, you have lower thermal performance.
Okay.
So what we've done here is this artery wick, which kind of acts to pull in water in the high heat flux regions of the GPU. So we have thicker wick on those sections and then thinner wick just where we can have extra thermal performance and reduce the net thermal performance.
Is there anything special going on with the top half here?
Yeah, so this, we use mesh, and mesh is typically a little bit lower capillary pressure, but higher flow rate. So we want to have high flow rate here and then higher pressure here. And then the braid is like a highway for water to come back. Really good in one dimension, but in 3 dimensions, you need something like mesh or sintered powder.
I don't know if this question even makes any sense, but what is the, I have no concept for how fast water condenses and evaporates in a system like this. I mean, like if you follow the same droplet of water or something.
Yeah.
Do you know how that process?
You can actually calculate the mass flow rate based on the power, and then you can just use the heat of vaporization to figure it out. But the speed of vapor, especially in the evaporator area, is incredible. It's like 10 to 20 meters per second.
Okay.
So,
all right, that's way higher than I thought.
Just
cool.
in the evaporator. But obviously, it slows down quite a bit as soon as it leaves the evaporator.
That makes sense. Yeah.
Yeah, and
Very cool.
The science of vapor chambers is incredible. There's sonic limits, like where you start getting compressible flow. It gets crazy. But, and all of those, you need to operate in a certain range in order to have the optimal thermal performance.
Very cool. Anything else on these you want to go over before we move to maybe liquid metal or something?
I think, this is basically just the evolution of the graphics card as we continue to refine it and continue to determine more stuff. And then finally we end up with, the final heatsink.
That's the actual final.
That is the final
okay.
dot two.
I see. So there's a
slight
protrusion.
pedestal. Yeah, it's about 150 microns, so only about 0.15 millimeter pedestal.
What's the purpose of that?
We just found it worked better with the barrier for the liquid metal.
Okay.
So
just to make sure you contact the silicon, I guess?
Exactly. You want to contact the silicon and then push down on the barrier.
Got it.
So
that's maybe a good jumping point to the barrier. So.
Yeah. So the barrier, this was something we've been working on for many years at this point. Even Ampere, we started looking at liquid metal. And obviously the thermal performance numbers are there, even at time zero. But the reliability is really the key part of liquid metal, making sure that it works in all environments, it works in all orientations. And you need to keep it in that GPU die region so that it doesn't electrically short anything or oxidize or have any issues in that regard. So what we've came up with is this hermetic seal rubber gasket here. And there was a lot of different trials, and we had different ideas on how to address all the concerns with liquid metal.
Yeah.
And we came up with this triple barrier rubber gasket here that basically seals to the heatsink.
When you say triple barrier, you talking about these ridges where
Exactly.
there's like 3 of them?
Yeah, exactly. Okay. So there's 3 ridges, and with this particular barrier, we've tested all orientation, shock and vibe, thrown the card around, and certainly no leaking, no degradation of thermal performance.
Did you have a loose barrier over here?
There you go.
Thanks. So I guess this is what you end up sticking on there around the GPU. Is this basically an adhesive, like a rubber?
Yeah, high temperature adhesive and then high temperature, low temperature silicone rubber.
Okay.
And then it covers all the capacitors around the GPU as well. So no local shorting, no PCB shorting, and no oxide formation.
Right. Okay. Is pitting a concern at all? I mean, if you're contacting nickel-plated copper, are there any relevant observable effects to that nickel,
the heatsink?
To the finish?
Yeah, so there's none with nickel plating. There's debate in the industry of whether copper is okay, bare copper, but we went with nickel plating because there's no real reaction there. Bare copper, there is visual black marks.
So a bit of a teaser for our Thermal Grizzly tour later, but Roman was just talking to me about this because he's got some kind of, I don't know, something in the works related to copper specifically as it contacts liquid metal. And if I remember correctly, I think he was saying that there is observable performance drop with time on exposed copper.
Yes, yeah.
Nickel plating, I think what he said aligns with what you said.
Yeah, because it is the gallium in there that reacts with the copper. And the interesting thing is, it also dries out the liquid metal because you're taking out the gallium, right? So that's why we went with nickel plating, where there's really no reaction.
What's the application process like? Is this machine applied at this point?
Yeah, this is machine applied, so we can specify the exact amount.
Okay.
The amount is really important to make sure nothing spills out, obviously.
Yeah, I guess it's been a while since we've made these liquid metal explainers, but one of the big things we would bring up back when delidding was very common was a lot of people go a little too heavy on it, and you can actually end up with worse performance.
Yeah, if you make it thicker.
If you make it a lake of liquid metal.
Exactly, exactly. Yeah, so it's a very fine balance between too little, too much, but we have really accurate dispensing process to make sure we have the exact right amount.
We're talking about endurance, and endurance, and then I guess orientation being important for you guys. So How do you approach endurance evaluation for something like this? And yeah, I guess what were sort of the conclusions? When you've made the final decision for liquid metal, what were the pros and cons you guys were weighing?
Yeah, I mean, basically this is what took us so long to make sure that this was a really reliable solution. We went through a lot of different prototypes. We tested in every kind of environment, high humidity, low temperature, high temperature. We cycle it, thermal shock, and then of course all the shock and vibe and all of that fun stuff. We've done kind of all of it. We've tried different barriers, and this is really the one that proved to kind of do well in every single one.
How does the difference manifest itself, I guess, from your best barrier versus like a single walled one? I mean, what are the types of differences you see? Actually,
the triple wall, it is a bit of an overkill, I think. We want to make sure, it's not going anywhere.
Yeah.
So we actually had a version with 2 and saw no issues, but when you can go for 3, why not go for 3?
Sure.
We did try a couple different ones, I have some samples over there. But, you start to see if there's any kind of hole in the barrier, or even if it can hold the liquid metal but it can't hold air, then you start to see either oxide or, in worst case, it could leak out, which is definitely what we don't want. So that's why we kind of went with this triple barrier. Even when 2 would have been enough.
Right. On the PCB, anything additional to cover? I mean, power delivery we're talking about a little bit.
Power delivery is incredible. Actually, even it's so interdesigned with the mechanical and thermal design that even the heat pipes travel through the spots between the inductors. That's why the inductors are where they are. So if you
that is cool. So they just run right there.
Yeah, exactly. Yeah. It's really a thermal, mechanical, electrical solution. Obviously, a really dense PCB, lots of memory. The chip has gotten bigger, more memory, and yet it's still like half the size.
Does the PCB layer count factor into your equation when you're designing the thermal solution?
Yeah, that and how much copper is in the PCB.
Okay.
So we have some ways to simulate that, and how if you add more copper below a certain component, you'll actually reduce that component's temperature significantly.
That makes sense.
So when we're doing our thermal solution, we can feed that back to the PCB designers, and then they can add more copper in certain places.
And then how about if we move over to this test board? So we've done stuff adjacent to this. I don't want to say like this, because this, for anyone in the audience who hasn't run thermocouple wiring, I find it to be incredibly frustrating. And I'm sure whoever did this must be in like a Zen state when they're doing it. But, because for me, I guess the things we look at are, you want to attach it ideally centrally on wherever the heat is generated on the component.
Yep.
You don't want to disturb the flushness of the mount. You don't want to disturb the thermal interface too much.
Yeah.
And then you also have this challenge of you got a bunch of wires.
Yeah.
And so this is like very difficult to do with this level of precision. But what types of things do you end up deciding to probe? I mean, do you just probe every component?
Yeah, actually, this is one of our earlier tests. So for the final version, we'll actually have about twice as many thermocouples along the entire PCB.
Yeah.
But again, the things you were mentioning, any tilt or imbalance, the application of thermocouples is an art. You know?
Yeah.
But how do we look at each component? We have simulation, obviously, so we want to try and correlate to that simulation, and also we want to validate that each component is below a given temperature. So when we look at it, we kind of look at areas we want to look at, and then specific components. And of course, in different workloads, each component is going to have a different amount of power going through it. So we meticulously look at each one and then thermocouple it, just to make sure that at the end of the day, every single component on this board, not just GPU, not just the memory, is well within spec.
So do you, I know at a consumer level even, we have some limited exposure to GPU temperature, right?
Yeah.
Hotspot temperature, and one that they just call memory temperature. And then I know the memory ICs themselves have temperature sensing that you can get access to.
Yep.
So where I'm going with this is, do you guys, are you able to just rely on the software polling of that and not have to probe, say, the back of the GPU or something?
Yeah, we obviously trust it, but we verify it as well. You know, especially with GDR7, we need to make sure everything is good there, right? And we verify it. And the readings are incredibly accurate, you know, when you compare it. Obviously, we're measuring case temperature and there's junction temperature, and there's a difference there. But whenever we correlate it back, you know, for G7 or for the GPU die itself, it's been incredibly accurate. And then also on, you know, we can look at the chip, for example, through IR imaging, just to make sure each sensor is correct.
Right. If you do that, how do you tackle that without the problem of the heatsink itself is in the way of what? I mean, do you just shoot the back of the board?
There's a method. I don't know if I could tell the method, to be honest.
That's fine. There's a method is enough.
It's quite incredible.
Okay.
There's a whole lab dedicated just to that.
I'll believe you, because last time I was there, you were measuring sound with lasers.
That is true.
Which was not something I knew you could do. So I'll believe you. Let's just walk over here for the last couple things you have. Where should we start with this stuff?
So this one was disassembled for you. Obviously, I haven't told you anything about it. So hopefully it goes well. It goes better than the prototype. But
I've seen that sticker before.
Oh, I wonder.
I mean, I don't
wonder where that one was.
I have not seen. Anyway, yeah. So you didn't tell me how you took this apart, which means we'll still do a teardown and I'll still figure it out blind. But
no drill is necessary, by the way. No hammers, but.
That's up to my discretion.
Each to their own. Each to their own.
These pads, NVIDIA's used these forever.
Yeah.
So you must like something about them or the team. What is it? Like what? Why these pads?
Mostly the reliability. So when we heat up the GPU, the whole board is kind of flexing. You know, the GPU is flexing. There's CTE mismatches or coefficient of thermal expansion. So you have all this, you know, movement inside there. And we've found that these pads specifically are incredibly resilient. They last a very long time. So that's why we continue to use them for this generation.
I guess you're trying to allow some of that movement?
Yeah. And we did, you know, last generation, we reduced it to 1.5 millimeter gap. So we kept that the same this generation just to make sure that temperatures still stay low.
Okay.
But this is the most reliable TIM we have, and we ship it on a lot of products.
What about the PCIe slot here? We saw the other side of this over there. I guess that's what sockets into it, and that's a custom solution?
That's correct. And then we have this part here that finally, you know, provides some
to just clamp it?
Yeah, to clamp it in with the screws.
Okay.
And then this part obviously connects to the main PCB. And then the I/O is actually connected here. So this is a flex, so it'll go like that and then plug in to the main PCB. So you can see that's the I/O and that's the PCB.
Are there any special considerations? Because like I/O I haven't seen done this way. I've always seen I/O attached to the rest of the card, right?
Yeah.
So is it challenging to run it this way? I mean, is signal integrity a big concern, or?
This is an incredible feat of engineering. Honestly, the signal integrity is a concern. Obviously, you know, you have your mechanical concerns, but this is, you know, UHBR20, DP 2.1. Incredible that we were able to put a connector. You know, all the specs and everything are made expecting no connector.
Right.
So when you completely revolutionize the cooling and the PCB architecture, you have to totally change, you know, everything. So a very high speed flex and, you know, the I/O over there.
Is there anything special to these, or are they just cover plates?
Actually, these are special. So basically, this is a pure aerodynamic change. So what we have this generation is we have incredibly effective fins beneath these covers. So these ones here, you know, if you look at 40 series or so, those were structural. So they had to be structural, and basically the fin pitch wasn't optimized. Here it's optimized, but we cover them with these covers that are structural. And then the beautiful thing is they're angled to reduce recirculation. So basically a pure aerodynamic change to redirect the airflow away from the inlet of the fan. So
There's-
actually airflow does go in
does it? Okay.
under there. So then
Okay.
the airflow, because it's not, the PCB is slightly larger than the fan. So then there is airflow here that is then redirected those directions. And then when that airflow exhausts, we have, we have these angled covers, which then direct airflow away.
That'll
from
be
the inlet.
cool. We'll try to see if Schlieren can show it.
Yeah, it'd be awesome. It'd be awesome.
Very
It's
cool.
actually, it depends on your case.
Yeah.
How close your exhaust is to the let's say the
glass.
glass.
Okay.
But the benefit can be huge. If it's really close, your benefit is going to be huge from that. If it's going straight out, then it kind of just, if it's far enough away, it won't recirculate.
Right.
But if the glass is right there, it'll go and it'll split 50-50.
Cool.
Half will go back in. So the reduction in inlet temperature to the fans is like 2 or 3 degrees.
Okay.
Incredible, actually.
Just from adding
from
these?
changing the angle from
Okay, cool.
from like straight
That's
out
actually really
to-
cool.
Yeah.
This might be one of the only pieces we haven't explicitly talked about. So this is the back plate, I guess.
This is the back cover, the PCB back cover. So the interesting thing here is we've increased the fin height on the back. Now, of course, that is an active fin area, but it is, passively cooling and radiating.
I feel it's got this rubber on it too.
Yeah.
So what's the story with that? Is that just a soft connection, basically? Or?
Exactly. And to make sure that, the fins aren't damaged during assembly.
Right. Okay.
And basically, this, we can connect the MOSFETs here, and then we have all this area for cooling the backside.
Yeah, it's funny. I've been complaining for years in videos about back plates that don't make use of the surface area.
Yeah.
So I'm happy to see it.
This is a really incredible one. I mean, it's the thickest one. It's the highest performance backplate, basically, because the PCB is lower in there. We started off, this is actually an Ampere card, and we tried different barriers, and this goes back into the barrier discussion. We evolved that. This is 40 series, 50 series, but we wanted to make sure that was the perfect solution, you know? Something that was really reliable, really met all of our criteria. So this is kind of just the walking through different prototypes, similar to how over there we have different heatsink prototypes. I kind of wanted to show the evolution.
This is going to look really cool with the first water block that can actually get to size.
Oh, it's going to be awesome.
Like it's going to actually be a cool display piece. So cool. That is the fairly deep dive, at least from a public perspective, look at the 50 series cooling. And I guess on our side, we just need to get to testing it once that embargo lifts. So we'll have that data soon. Malcolm, thank you very much for your time and patience.
A pleasure. Yeah, 5090, 2 slots. I think, even 5 years ago, if you would have asked me, I would have thought it was impossible.
Yeah.
But, when you look at each resistance along the way, optimize each one, you come up with something that's really beautiful. So, it's an incredible card.
Yeah, I'm excited to test it. And then if you want to see other videos Malcolm's been in, I'll link them below. All of them are just as interesting, even if the products have aged a little bit, so you should check them out. But thank you for joining me, and we will see you all next time.